Have you ever just stopped and wondered how we taught computers to do something so human? Like, how did we teach a machine to understand language? It's this incredible story, a real journey of rules and revolutions and just tons of data. And today, we're going to dive right into it.
I mean, really think about it for a second. That little predictive text on your phone, or how your email magically knows which messages are spam, or when you can translate a sign in another country just by pointing your camera at it. It feels like magic, right? Well, it's not magic. It's something called natural language processing, or NLP, and it is quietly running pretty much everything. So, what is it exactly?
Well, to put it simply, NLP is a field of AI that's all about one thing: bridging the gap between how we talk and how computers think. It's about giving machines the ability to read, understand, interpret, and even generate human language.
To really get where we are now, we've got to go way back to the beginning. See, this wasn't some overnight success. It was a slow, steady evolution that started with a very logical, very human idea. If you want a computer to understand grammar, you have to teach it the rules of grammar.
So, our story kind of breaks down into three big chapters. First, you've got the age of rules, where programmers basically tried to write a giant grammar textbook for computers. Then came the statistical revolution, where we decided to let the data do the talking. And finally, that brings us to the modern era of machine learning, where computers started to learn in a way that's, well, a little more like us.
Let's throw it back to one of the earliest pioneers, a chatbot from 1966 named Eliza. It was designed to act like a psychotherapist, and it worked with a bunch of hand-coded rules. So if you typed, "I am sad," a rule would kick in, and it would spit back something like, "I am sorry to hear you are sad." It was clever for its time, but it didn't understand a single thing. It was just a script. And that right there was the huge roadblock with this whole rules-based approach. Human language is messy. Think about the word bank. Are you talking about a riverbank or a money bank? You'd have to write a specific rule for every single context. It was totally impossible to scale. You just can't write a rule for every single way we humans have of saying something. So after a while, researchers had this really radical idea. What if we just stopped? What if instead of trying to teach the machine every single rule by hand, we just showed it millions and millions of examples of language and let it figure out the patterns for itself? And that was the big shift. Okay, so one of the very first attempts at this was a super simple idea called bag of words. You literally imagine taking a sentence, throwing all the words into a bag, shaking it up, and then just counting what you have. It completely ignores grammar and word order. It's basically word soup. And it's surprisingly useful for simple tasks. But as you can imagine, you lose a ton of meaning. For example, in a bag of words model, the phrases not good and good not, they look exactly the same, which is, a problem. To fix this, developers came up with something called n-grams. Instead of looking at single words, they started looking at pairs of words, or triplets, to keep at least some of that local context. Here's how it works. An n-gram model sees a phrase like, "this is a," and based on all the books and articles it's ever read, it calculates the probability of what word comes next. Sentence would have a really high probability. And this simple idea? This is basically the granddaddy of the autocomplete on your phone. N-grams were a huge leap, for sure, but they had a major flaw: a really, really short memory. They could only look back 2 or 3 words. But we all know that in language, a word at the very beginning of a sentence can completely change the meaning at the very end. So how could you get a machine to remember that long-range context? Well, the answer came from an architecture inspired by the one thing that's best at language: the human brain. We're talking about neural networks. Specifically, a type that was designed to handle sequences and to remember. These are called recurrent neural networks, or RNNs, and the magic is that little loop you see in the diagram. As the network processes each word, it feeds a little piece of information back into itself. It's like it's whispering to itself, passing a note from one word to the next, creating this chain of memory that carries context through the whole sentence. But even RNNs weren't perfect. Their memory was, it was kind of leaky. For really long sentences, they'd start to forget what happened at the beginning. The fix was an upgraded version called an LSTM. Think of it like an RNN with a really sophisticated memory controller. It uses these special things called gates to decide what information is a VIP that gets to stick around and what can be forgotten. That little tweak, adding gates, was a total game changer. So for years, RNNs and LSTMs were the kings of the NLP world. They were state of the art. But then in 2017, everything, and I mean everything, changed. A brand new architecture came out that didn't just improve on the old ideas, it blew them out of the water.
It arrived in a research paper with a title that was both incredibly simple and honestly kind of bold. Attention is all you need. This paper introduced the world to the transformer architecture, which is the foundation for pretty much every massive AI you hear about today, from BERT all the way to GPT.
So what made transformers so special? Okay, first, they were ridiculously fast. Instead of reading a sentence one word at a time, they could gulp the whole thing down at once. Second, this attention mechanism let them see how every single word in a text related to every other word, no matter how far apart they were. And that combination of speed and smarts made them unbelievably scalable. For the first time, we could build truly enormous AI models, and that unlocked the power we're seeing all around us today.
And that brings us right back to now. This tech isn't hiding in research labs anymore. It is everywhere, woven into the fabric of the tools we use every single day.
Take named entity recognition. You know when you read an article online and it automatically tags the people, places, and organizations? That's modern NLP, scanning and structuring information in the blink of an eye. It's also how we bridge the gap between the physical and digital worlds. Think about scanning a receipt with your phone to get an expense report started. That's optical character recognition, and it's powered by NLP. And maybe the most mind-blowing part is that it's moved beyond just understanding language to creating with it. Today's models can now write working software, actual computer code, from a simple sentence you type in plain English. It's wild.
I mean, just step back and look at that arc. We went from machines that could only follow simple, pre-written rules to models that can act as our technical and creative partners. So let's just nail this down one last time. NLP started with rigid, hand-coded rules. It evolved to learning from data with statistics. Then neural networks gave machines a kind of memory to understand context. And finally, the transformer architecture unleashed the massive scale and power we're all experiencing today.
So, we've seen how machines learn to write, but here's a final thought for you. We've talked all about how machines process language, but we kind of skipped over the very first, most fundamental step. Before a model can do any of this, it has to turn our words into numbers. So we know they can write, but how do they actually read? That's a story for another time. Thanks for joining us.